We're going to cover this on Tuesday if we have time, but just since I have the slides ready, I thought I'd record it now if you wanted to get ahead. The law of total probability is way cool. Let's suppose I have an infinite, finite or countably infinite family of events. So you can think of events like you recall the roulette wheel spinning, and I'm looking for the different number of sequences till I reach 36. So I could say the event is B1 has to have trying to think of something that would be independent. B1 is the event with the sequence that contains a 1 in it. B2 is the event that a sequence contains 2 in it, but not 1, and so forth. So, so they have to be mutually exclusive, meaning that they can't share an element, and they have to be exhaustive, meaning that the union of all of these guys equals the total sample space. So basically, you're partitioning the sample space. If A is any event, then the probability of A can be broken up into these sub-probabilities, like probability of A intersect B1, ... This is actually pretty fairly straightforward to prove. And in class, maybe on Tuesday, I'll go through your first proof with a checklist and everything to show you how to do that. But this is one that you can use the properties of probability and prove it. There's a beautiful picture in 71. I tried to make a picture, but let's suppose I had B1, B2, B3, and I had this A, and this is B4. I forgot to label it. A is really B1 intersect A, and there's B4 intersect A, and there's B3 intersect A, and B2 intersect A. So the blue, the green, the turquoise, and purple make up all of A. So if I wanted the probability of A, I can just take the probability of the blue, plus the probability of the green, plus the probability of the turquoise, plus the probability of the purple. So pictorially, it's easy to intuitive to explain. Bayes' rule is also in this section. I'm going to assume everything as in the previous theorem, mutually exclusive, blah, blah, blah. Then if I have the probability that BJ of BJ given A is equal to the probability of A given BJ times the probability of BJ times this sum, which seems crazy. And what this sum is, I don't like summation notation. I like to see it written out. It's probability of B1 times probability of A given B1 and so forth. I'm going to show you how to use this because this formula seems crazy, and you would think, well, why would I ever use it? What am I ever going to use this for when you see something nutty like that? This probability is sometimes called a posteriori probability, not posterior, because posterior means but. So you can think of it as the but probability rule. But I'm going to show you an example from Robert Ashe. Posterior means your butt, your rear, or something to the rear, right? So you're back calculating, basically. So 2 coins are available. One is unbiased and the other one is two-headed. Suppose I choose a coin at random and assume that the unbiased coin is chosen with a probability of 3/4. Suppose I know the end result, the but result is heads. Find the probability that the two-headed coin was chosen. Well, how could I have arrived at that? There's tree diagrams in your book. So you see me drawing a tree diagram. In the Bayes' rule section, they have a tree diagram. So if I choose a coin first, I have a 3/4 chance of choosing the unbiased coin and a 1/4 chance of choosing the biased coin. Then, after I choose the unbiased coin, I have a half chance that I could get a heads and a half chance to get the tails. If I selected the biased coin, I would get a 1 whole chance of getting a heads, because it's a two-headed coin, and a 0 chance of getting the T. So B2 is the two-headed coin is selected. A is that the coin comes up heads. These are my events. If I apply Bayes' rule, Bayes' rule says that probability of B2 given A is equal to this, which is equal to this, and probability of A is given by that summation formula. I take the 3/4 times a half plus 1/4. So which path am I going? I could get to heads this way, or I could get to heads this way. And that's a 2/5. So I have a 2/5 chance that the two-headed coin, given that I know that it came up heads, that the two-headed coin was selected. So that's how this is used. These formulas are used. Your answer is usually given at the end. You know your answer, and you're back calculating the probability it could have come down that path. So you would think that this is pretty crazy, and that nobody would do this. But I actually have used this. I've seen this. A colleague of mine was looking at, when you have a baby, what you really know is what happened at the end, because you really cannot see in utero that well. Yes, you can look inside with ultrasounds, but at least American women feel that MRIs are unsafe, and so it's really hard to look at the baby during the growth period and see what happened. So what we have is the end result. And there was a theory that when something goes wrong, it's because the placenta moves around in utero. He proved that it cannot be so. The probability of that happening, which it's something more complicated than that, but he was going in back calculating the probability of each of these different events happening, and it couldn't be so. So it's a beautiful paper by Michael Jablonski and Carrie Salafia, where they use this idea of going back and trying to estimate the probabilities.